Hi, Chem 101 students. Welcome to the last lecture on the Silverberg textbook, chapter 18. This is acid-base equilibrium. And so in the last couple of lectures, we talked about kind of just a review of acids and bases and some new ideas like how we can look at the formula for an acid and figure out its relative strength compared to others. In the second lecture, we used the Ka and the initial concentrations to determine the pH of a solution. We also did the same for Kb and the initial concentration of a base to determine the pH of the solution. So now what we're going to start to do is look at the calculating the pH of a salt solution. Now, one thing that you'll notice if you look at Appendix C is that you are given a series of and I'll just kind of point that out here. Let's take a look at Appendix C, which is also posted in your Canvas if you want to print that out. It's of course also in your book. So here's the Appendix C, and when you look at Appendix C, what you're going to see is that there are of course Ka1s, Ka2s, and 3s for polyprotic acids, as we discussed in the last lecture. But all of these are Kas for neutral acids. Neutral acids. None of these have a charge, notice. And in addition, so we go through all the acids here, lots and lots of different acids. And then when we look at the Kbs, we have Kb for a variety of neutral bases. None of these bases have a charge to them. You'll notice they almost all have nitrogen atoms, a nitrogen atom, and its lone pair that can be donated is the base in this reaction, or for these bases. The nitrogen atom is essentially acting as the base and accepting the proton. So you'll notice these are all neutral as well. There are no Kas or Kbs provided for ions. However, ions can behave as acids or bases. As we have seen, they can be the conjugate acid, an ion can be the conjugate base to an acid, or a positive ion can be the conjugate acid to a base. And so if we want the Ka or the Kb for an ion, what we're going to have to do is calculate it from known Kas and Kbs for neutral acids and bases. So the formula we use for that is that the Ka for an acid times a Kb for its conjugate base is equal to Kw. And so we can, if we're and remember Kw is simply the number at 25 degrees Celsius. It's 1.0 times 10 to the minus 14 at 25 degrees Celsius. So what we can do is, if we have tables of Kas and Kbs like we have in Appendix C, we can determine the Ka or the Kb for a conjugate acid or base. Whoops, I copied over that, but yeah, it says the same thing. So now it's there. All right. Okay. So what this means is if we divide both sides by Kb, we get that the Ka is Kw over the Kb, or if we want Kb, the Kb will be the Kw over the Ka. And again, this applies to a conjugate acid-base pair. Also, a related equation is if you add pK and pKb, they add up to pKw, which is 14, the negative log of 1 times 10 to the minus 14. Here, and this for some reason has a positive here. This should definitely be minus. Okay. And so we're going to use this fact to calculate Kas and Kbs for ions. So the reason why we want to do this is because if you dissolve salts in solution, those ions may behave as acids or bases. And so we can see here, this is a series of various salt solutions with universal indicator in them to indicate the pH. If you have sodium chloride dissolved in solution, this results in a neutral solution. Sodium is not acidic, chloride is not basic. It's just a neutral solution. However, if you have ammonium chloride, the ammonium ion here the ammonium ion in here, NH4 plus, is the conjugate acid of the weak base ammonia. And so it can behave like an acid, and we're going to see that for solutions containing ammonium ion, they are acidic. The pH is less than 7. In addition, there are some metal ions, highly charged, small in radius metal ions, that also can behave as acids. And so those will result in a solution that is acidic or pH less than 7 either. For this example here, sodium cyanide, this one contains a negative ion, cyanide ion, which is the conjugate base of the weak acid HCN. And so this cyanide ion will actually itself be able to behave as a base to some extent, and that will result in a basic solution with pH greater than 7. And then this solution here has a mixture of an acidic cation, NH4 plus, which is acidic, and a basic anion, carbonate ion, which can act as a base, as we'll see. And so the pH in a solution that has both an acid portion and a basic portion will depend on how strong is the acid portion compared to how strong is the basic portion as a base. And so we'd have to compare the acidity of the acid versus the basicity of the base to determine the pH. So if we want to determine, if very simply, if a salt solution is acidic, basic, or neutral, there is a kind of simplified recipe we can use to do this. This is the same recipe I teach to like my intro chem students. It's a nice quick way of kind of explaining with something that can be easily memorized, whether a salt is neutral, basic, or acidic. But it is also important that you understand the concept behind why, and so we'll be discussing that as well. If you have a salt that could be produced from the neutralization of a strong acid and a strong base, that salt will result in a neutral solution. If you have a salt that could be produced, a salt meaning again an ionic compound that is not a hydroxide, if you have a salt that can be produced from a strong acid and a weak base, this will make a salt that makes an acidic solution. And if you have a salt that can be produced by the neutralization of a weak acid and a strong base, that salt would make a basic solution. So that's a kind of quick recipe that you could use to figure out if a salt is acidic, basic, or neutral. It doesn't really help you with understanding why it's acidic, basic, or neutral, but that is a strategy that you can use. What is better is to think about the ions in themselves and whether they're acidic, basic, or neutral based on their conjugate acid or base. So you may remember from the last lecture, we said that the stronger an acid is, the weaker its conjugate base. And the stronger a base is, the weaker its conjugate acid. And that's the idea that's going to be very useful to us in deciding if the ions that are a part of a salt produce acidic, basic, or neutral solution. And so salts that produce neutral solutions are those cations that are from strong bases, such as group 1 cations, and alkaline earth metals, such as calcium, strontium, barium. It does not include beryllium because beryllium hydroxide is not very soluble. In fact, magnesium hydroxide is not very soluble either. And then for salts that yield neutral solutions, neutral anions are those from strong monoprotic acids such as hydrochloric acid, which has bromide ion, hydrobromic acid, which has bromide ion, chloride ion, iodide ion, nitrate ion, hypochlorite ion, or perchlorate ion rather, sorry. And so this goes back to what I was telling you about the salts that are neutral. For example, sodium chloride are those that could be produced by the neutralization of a strong acid and a strong base. The strong base here would be sodium hydroxide, and the strong acid would be HCl. And so the cations from strong bases produce neutral salts, and the anions from strong acids produce neutral salts. And this is because to explain why here, especially for the anions, what we know is a strong acid like HCl dissociates 100%. So it makes HCl and chloride minus. And so this here is a strong acid. And that means this goes 100% this way. And what that means is that it does not go really at all. If we're talking about the backwards reaction here, this doesn't really go at all. And so a chloride ion is never going to go and accept protons. So because this is such a strong acid, this is a terrible base. This is an extremely weak base. So this anion is not going to be a basic anion. And notice it's generally going to be cations that could potentially be acidic. It'll be anions that could potentially be basic. This makes sense, right? It's because anions could more easily pick up an H+, since they're negative and H+ is positive. Cations could potentially have a H+ to give away. Or, as we'll see in another example, there are other ways in which cations can be acidic. But these anions, these negative ions, are the anions that are the conjugate bases of strong acids, so they themselves are terrible bases. And all of these group 1 and group 2 cations, they are not good acids. We are going to see other cations that are decent acids. So let's move on. So group 1 and group 2 positive ions do not produce an acidic solution. And anions that are from strong acids, part of strong acids, are not basic. They produce neutral solutions. So let's talk about some types of ions, positive ions generally, that could produce acidic solutions. So those are going to be the conjugate acids of weak bases. So here we have ammonium ion. That is the conjugate acid of the weak base ammonia. And so it has an equilibrium with ammonia. So if you put ammonium ion in water, it can give its proton to water, and then what you get is hydronium ion and ammonia. So ammonium ion is the conjugate acid of the weak base. Since the base is weak, its conjugate acid is at least not terribly weak, right? If the base is strong, then its conjugate acid will be terribly weak. But since this conjugate base ammonia is weak, the ammonium ion can behave as an acid because there's an equilibrium between the weak base ammonia and its conjugate acid ammonium ion. So that ammonium ion can give up some protons and behave like an acid. So any protonated nitrogens here, protonated meaning they have a proton attached, the conjugate acids of weak bases like ammonia will form acidic solutions. Then there's another class of cations that can form acidic solutions, and those are transition metal cations generally. They are those that are highly charged and small. So we're talking at least +2 in charge and generally near the top of the periodic table. So the quintessential and kind of perfect example of this is aluminum. Aluminum is near the top of the periodic table. It's extremely small in radius, but it has a very high +3 charge. When you put it in water, it makes a transition metal complex with water, where the water is the ligand here. So the water makes coordinate covalent bond with aluminum, and we get this hexaaqua aluminum complex. Now, this aluminum ion is very small and it's very highly positive. And what that means is it's pulling electrons very strongly towards itself. And here's the result of that. Since it's pulling those electrons so strongly towards itself, it weakens the bonds between the oxygen and the hydrogen by the inductive effect that we discussed earlier. And so this oxygen-hydrogen bond can very easily break and release an H+ ion. And so this comes off as an H+ ion and it attaches to water. So small, highly charged metal ions can behave as acids in this fashion. It's because they attract water molecules as ligands. Their very strong pull on electrons produces an inductive effect, which weakens the bond between the oxygen and the hydrogen in a water ligand, and then one proton can come off, and then this complex here is behaving as an acid. If we go back to the appendix, you'll actually see that for a variety of transition metal cations like iron 3, so these are all acidic cations here, they are actually provided at Ka. And they're cations again because they become hydrated by water, and their pull on the electrons weakens the bond between oxygen and hydrogen in a water ligand, and then an H plus is released, and so that's how these behave as acids. And notice these are all ions that are high up on the periodic table. They're in like the 4th row. None of these are below that. And also they have at least a positive 2 charge. Oftentimes positive 3 is even more acidic. So you can see here the aluminum and the chromium here are both positive 3, very, very acidic, high Kas, relatively speaking, compared to those that are positive 2. All these are positive 2, much lower Kas. It's because it's related to the charge on the metal cation, the fact that it's high in charge and small. Now, when I ask you questions about this, I tend to focus on the extremely small and highly charged cations. So these include beryllium and aluminum. So aluminum being the best example here. Lithium, this is not acidic because it's, well, one way we can see is because we saw earlier that it's the cation that's a part of a strong base. Also, it's just not highly charged enough. It's only positive 1. The positive 1 ions are never going to be acidic. Their charge just isn't high enough. Magnesium ion will be somewhat acidic, but aluminum will be much, much more acidic. The higher the charge, the more acidic it is. As you can see again, if we go back here, we see that those that are positive 2, lower Kas, those that are positive 3, much higher Kas. Like iron 3 plus is quite acidic as well. It's the most acidic out of all of these. So, and then salts that are going to make basic solutions. So those will be salts that contain a negative ion that is the conjugate base of a weak acid. So salts such as sodium cyanide, which are derived from the neutralization of a strong base and a weak acid, these yields basic solutions. And the reason behind this is that the cyanide ion itself is the conjugate base of the weak acid HCN. So this is a weak acid. And so that makes the cyanide a decent base. Now, as we discussed previously, if we have a strong acid like HCl, there's no equilibrium here. And so this reaction, if we had, if this were HCl instead right here, and this were chloride ion, this reaction would not go, and we have water, of course, this reaction would not go in the forward direction because HCl is a strong acid. It completely separates from chloride. It only goes in the direction where it stays separate from chloride. But that's because HCl is a strong acid. HCN is a weak acid. So there's an equilibrium here. And this cyanide can behave as a decent base, and it can grab a proton from the water. And so we're writing the equation of cyanide acting like a base. It's accepting a proton from water, and then it produces its conjugate acid HCN, and what's left of the water is hydroxide. And so anions, negative ions that are the conjugate base of a weak acid, will behave as a fairly decent base. The stronger the acid, the weaker the conjugate base. But for a weak acid, the weaker the acid, the stronger the conjugate base. And so this is a decent base here. Overwrote my words there. But cyanide ion is the conjugate base of the weak acid HCN. Sodium is neither acidic nor basic. Again, it's a positive 1 ion. Those are never going to be acidic. Finally, what if you have a salt that has both acidic cations and basic anions? Then how do you decide if it's going to make an acidic or basic solution? Well, if we have one like ammonium carbonate here, so this has an ammonium ion. The ammonium ion is acidic because it's the conjugate acid of the weak base ammonia. And the carbonate ion is basic because its conjugate acid, so its conjugate acid here is HCO3 minus, which definitely is not a strong acid. So it's the conjugate base of an extremely weak acid. So carbonate is very basic. So we want to ask ourselves, is a solution with ammonium ions in it and carbonate ions in it acidic or basic? To evaluate that, we're going to have to figure out how acidic is the cation and how basic is the anion. And the way we can evaluate that numerically is by calculating the Ka for the ammonium ion and the Kb for the carbonate ion. If the Ka is larger than the Ka for the acid, is larger than the Kb for the base, then the solution will be acidic. But if the Kb for the base is larger than the Ka for the acid, then the solution will be basic. So what we need to do is we need to look at the acid reaction. And so this is the ammonium acting like an acid. Again, writing the equations for an acid acting like an acid or a base acting like a base is usually the hardest and newest part of these problems. So you definitely need good practice doing that. So the ammonium ion is an acidic cation. So it's going to donate its proton to water, which means that it produces hydronium ion, H3O+, and then what you get left is the conjugate base of the ammonium ion, which is ammonia. And so what we'd like to do is get the Ka for this reaction. However, as we discussed earlier, our table does not include the Kas for ions. What we're going to have to do is use the Kb for its conjugate base to figure out the Ka of the ammonium ion. Likewise, carbonate ion behaving like a base means that it is accepting a proton, so the water is giving the H+. And so the result is that this carbonate has one more H and the charge goes up by 1 from 2 negative up to -1. And what's left of the water is hydroxide. It lost 1 hydrogen and the charge went down by 1 unit from 0 down to -1. Okay, and again though, this is a negative ion. Our Appendix C does not give us the Kb's for ions. So we're going to have to determine this based on the Ka of its conjugate acid, carbonic acid, which is in fact the Ka2 of carbonic acid. So we'll break that down on the next slide, but there's 3 possibilities here. If the Ka for the ammonium ion is greater than the Kb for the carbonate ion, then the solution will have more hydronium ions and hydroxides, so it will be acidic. The pH will be less than 7. If the Ka is smaller than the Kb, then the Ka of ammonium ion is smaller than the Kb for carbonate ion, then the solution will have more hydroxide ions than hydronium ions. The pH will be greater than 7, and it will be basic. If the Ka and the Kb are close together, close to one another, the solution will be about neutral. So the hard part is going to be determining the Kas and the Kb's for these ions. So one note here is that if we're trying to figure out the Ka for bicarbonate ion, this is in fact the conjugate base of carbonic acid here. So the K for this reaction right here, this is going to be Ka1 for carbonic acid. And then the K for this reaction right here, which is the reaction we're interested in, is going to be the Ka2 for carbonic acid. And so we're actually interested in this blue reaction here because we want to know the Kb for carbonate, which means we need the Ka for bicarbonate ion, which is the Ka2 of carbonic acid. That's how we're going to look this up on the table. Okay, so let's figure out the Ka for ammonium ion. We're going to need the Kb for ammonia. So the Ka for ammonium ion is going to be Kw over the Kb for ammonia, which is its conjugate base. So if we go to the appendix C, we can find the Kb for ammonia. It is about 1.8 times 10 to the minus 5. We got one extra sig fig on that, but so Kw is 1 times 10 to the minus 14. We're going to divide by the Kb for ammonia, which is about 1.8 times 10 to the minus 5. And so now let's break out our calculator and divide this. 1 times 10 to minus 14. Divide by 1.8. It's 10 to the minus 5. And we get about 5.6 times 10 to the minus 10. So that is the Ka for ammonium ion. Again, we have to use this relationship because we are not going to be given in a table the Ka for ions. We have to get the Kb here for the conjugate base of this positive ion. Likewise, we do not have a table with the Kb for carbonate ion. What we need to do is we need to find it from the Kw and the Ka for bicarbonate ion. And again, the way this is going to look on the table is this is going to be the Ka2 of carbonic acid. That is the Ka for bicarbonate ion. So we go to the appendix here, and we look for carbonic acid right here, and we want the Ka2. So that will be, so this is the Ka for carbonic acid right here, and this is the Ka for the bicarbonate ion. And so we want this one, 4.7 times 10 to the minus 11. So we're going to plug that in now. So we got Kw on top, and we've got, again, whoops, that's not right. Oh, it's different. Okay, well, we can fix this right now. Let's do it. I think what happened was it changed, actually. So we'll put in 4.7 times 10 minus 11. That's fine. 4.7 times 10 minus 11. Now let's fix this. Let's calculate it. And I'll upload these changes here as well. 1.0 E 14 minus, and then divide by 4.7 E minus 11. And so we get, we'll replace this with 2.1 times 10 to the minus 4. So 2.1 times 10 to the minus 4. Either way, we can see that this carbonate ion is much more basic than the ammonium ion is acidic. Its Kb is way larger by about 1,000,000 times than the Ka for ammonium. So this solution is definitely going to be basic because the Ka for the ammonium ion is less than the Kb for the carbonate ion. So in summary, how can we identify what's going to be acidic, basic, or neutral? So for a salt that has the cation from a strong base, such as sodium or barium, any of the group 1s or group 2s, and an anion from a strong acid, this is going to be a neutral salt. If it has the cation from a weak base, for example, ammonium ion, which is the cation that is the conjugate acid of ammonia, a weak base, but it has the anion from a strong acid, such as chloride from hydrochloric acid or nitrate from nitric acid, this is going to be an acidic solution. Here. If we have a small highly charged cation, such as aluminum 3+, chromium 3+, or iron 3+, that's going to be an acidic cation. If the anion is the conjugate base of a strong acid, like chloride ion, whose strong acid is HCl, or nitrate ion, whose conjugate acid is HNO3, or perchlorate, whose conjugate acid is HClO4. Then we have a acidic cation and a neutral anion, so this is going to be an acidic solution. If we have the cation that is from a strong base, meaning it's group 1 or group 2, these are not going to be acidic. And if we have an anion that is the conjugate base of a weak acid, that anion will be basic, and so the solution will be basic. Finally, if we have an acidic cation that is the conjugate acid of a weak base, and a basic anion, which is the conjugate base of a weak acid, we're going to have to figure out how acidic is the cation versus how basic is the anion. and that will help us to determine whether the solution will be acidic or basic. But we can go one step further here. We can actually calculate the pH of a solution of a salt, assuming that it is not, we don't have the competing effects of an acidic cation and a basic anion. So here we've got ammonium chloride. So this is composed of ammonium ion, which is an acidic cation. It's the conjugate acid of the weak base ammonia. And we have an anion, chloride ion, that is a neutral anion because it is the conjugate base of the strong acid HCl. So we want to calculate the pH of a 0.5 molar solution of ammonium chloride. The only ion we care about is the ammonium ion here because that is the acidic one. The chloride ion is neutral, it's not going to do anything. And we already determined the Ka of ammonium ion. Previously it was Kw over the Kb of ammonia, and so that was 5.6 times 10 to the minus 10. Okay, so what we do, if we want to find the pH of the salt, we do it the same way as if we were finding the pH of any other weak acid. This ammonia is a weak acid, this ammonium ion. So we're going to write the equation for the ammonium ion behaving like an acid. So ammonium ion is acidic because it's the conjugate acid of a weak base. Chloride ion is neutral because it's conjugate base of a strong acid. So we write the equation for ammonium acting like an acid. So we have ammonium ion in water. We don't care about the chloride ion because it is neutral. So it's neutral, so we don't care. We care about what's acidic here. So that's going to affect the pH. And so it's acidic, it's going to give its proton to water. And we're going to have an equilibrium here where we have the conjugate base of our ammonium ion, which is ammonia after it has lost the H+, and we have hydronium ion, which is the conjugate acid of water after it has gained one H+. So just like if we're trying to figure out the pH of any other weak acid solution, we've got the Ka, we're going to use it, we got to set up an ice table and state our equilibrium concentrations in terms of X. So we set up an ice table, and ammonium ion concentration is right here, 0.5 molar. And our ammonia concentration is 0 to start, and our hydronium is close to 0. Of course, there's always a little bit of hydronium in water, but we're going to assume that it's negligible. Now, because there's no products, this reaction can't go backwards, it has to go forwards. So we're going to put minus X here, we're going to plus X here, and plus X here. And then for our equilibrium concentrations for ammonium, it will be 0.5 minus X, and it will be X and X right here. Okay. So now we're going to write the Ka expression for this reaction. So again, just products over reactants. So the Ka here is going to be ammonia times hydronium concentrations on top. On the bottom will be ammonium ion concentration down here. And this is going to be equal to the Ka of the ammonium ion. And we're going to plug in now our equilibrium concentration stated in terms of X. We plug in X for ammonia, and we plug in X for hydronium. Then for ammonium ion, we plug in 0.50 minus X right here. And those are going to be equal to the Ka, which is 5.6 times 10 to the minus 10. So we're going to take this over to the next slide. So we got x times x over 0.5 minus x is 5.6 times 10 to the minus 10. And what we're going to want to do is we're going to want to do a pre-check here. Okay, as usual, we want to make sure that our K is small enough that our X is going to be very small. So we take our initial concentration and divide it by the K, and we want to make sure this is greater than 400. It is far greater than 400. We don't even need a calculator for this. It's like a billion. So we're very safe here on our pre-check. So we can assume that X is very small. So 0.5 minus X is going to be just 0.5. So yeah, because when we subtract X from 0.5, it basically doesn't make a difference in the 0.5. So now we're going to set Ka equal to that. So we have x times x squared over 0.5, and that is equal to Ka, which is 5.6 times 10 to the minus 10. So now we're going to multiply both sides times 0.50, 0.50. So that's going to cancel 0.5 here. And if we plug in 5.6 E minus 10 times 0.5, we get 2.8 times 10 to the minus 10. And that equals x squared. Now we have to take the square root of both sides. So we square root x squared, we get x. And we square root this. So square root. And we get 1.7 times 10 to the minus 5. So x equals 1.7 times 10 to the minus 5. And that is our hydronium concentration. So now to figure out the pH, all we got to do is take the negative log of that. So we do 1.7 E minus 5. Oops, I didn't type that right. 1.7 EE minus 5. And we're going to take the log of that and then change the sign. So we get, for that, we get 4 point, and remember, we want to write this with 2 after the decimal because we took the log of a number with 2 sig figs. So our result will be 4.77 for the pH. The negative log of that, we get 4.77. And that is the pH. And so that is how you find the pH of a salt solution. So the big difference between doing the pH for a salt solution versus doing the pH for a weak acid or a weak base is that you're not going to be able to look up the Ka or the Kb directly from your Appendix C. Instead, you're going to have to identify the conjugate acid or base and use that to figure out the Ka. So like we did here with ammonium ion, we said that the Ka is going to be Kw divided by the Kb for ammonia, and that's how we got the Ka. So that's the one extra step you have when you're dealing with a salt, is you've got to figure out the K based on the K for its neutral conjugate. Finally, the last topic in this chapter is Lewis acids and bases. So in our Bronsted-Lowry definition, we say that an acid is a proton donor and a base is a proton acceptor. And so it makes acids and bases all about proton donation and accepting. And that is generally a very good way and a very convenient way to define acid and base. However, there is a broader definition that is also used, and this is the Lewis definition. And this definition is so broad, it can be extended to include many, many different types of reactions that don't, on their surface, look to be acid-base reactions. And so the definition of a Lewis acid is an electron pair acceptor. And for a Lewis base, it's an electron pair donor. So the reason why this definition came about is precisely related to the fact that small, highly charged cations like aluminum behave as acids. The way they behave as acids is they accept water as ligand. So the water is the electron pair donor, it's the base. The acid is the electron pair acceptor. The aluminum is the electron pair acceptor, it's the acid. And so we end up with this hexaaqua aluminum complex, and then ultimately one of these oxygen hydrogen bonds breaks and we get an H plus out of it. Here's another example of a Lewis acid base reaction. We already consider ammonia as a base, but the way it's behaving as a base with this copper ion, which is the Lewis acid here, is that it is donating its electron pair directly to the copper. And so again, this expands the definition of acids and bases to include many different reactions that you may not have initially have thought of as acids or bases, acid-base reactions, because you didn't see a movement of a proton. But instead, it's the donation of the lone pair in a coordinate covalent bond that defines the Lewis acid and bases. So when we studied chapter 23 right before the exam, all of the ligands are functioning as Lewis bases. They are donating a lone pair. And all of the transition metals are functioning as Lewis acids. They're accepting the lone pair. So you can see the result here. And this is a result we're going to use as we start to go into experiment 13 next week. It's going to affect the solubility of a variety of transition metals, which will help us to separate them. So what we see here is we have a light blue solution of copper ions. Then we add ammonia, which functions as a Lewis base. Ligand here attaches to the ammonia. And ultimately, what's produced in a somewhat complex process is copper 2 hydroxide, which is insoluble. And so it comes out of solution here. If we add more ammonia, though, then we force the production of this tetraamine copper 2 complex ion, and ions are soluble. So this neutral hydroxide is not soluble, but if we add even more ammonia, we'll produce this soluble complex ion, and then it has a deep blue color to it. Also a very important Lewis acid base reaction is one that occurs in the atmosphere with pollutants. So one example pollutant is sulfur trioxide. So this is produced often when we burn coal. When they talk about clean coal, they're talking about coal that has less sulfur in it. So it produces less sulfur trioxide. It does not mean that it produces any less carbon dioxide, although I'm sure it's meant to be misleadingly seem like it does. It does not. If you burn something, that produces carbon dioxide, but it does produce less sulfur trioxide. And sulfur trioxide is a concern because it can function as a Lewis acid, the sulfur, and accept a lone pair from water. And ultimately, you end up making a bond between the sulfur and the water, and we get a little bit of a rearrangement here of the bonds, and ultimately this produces sulfuric acid. And that's bad. We don't want sulfuric acid in the atmosphere like this, and it rains down in the water, and that's called acid rain. There's a number of other reactions that result in the production of acid rain. It's nitrogen dioxide is also often produced from combustion. It can react with water to produce nitric acid in this way. Again, the NO2 here would be the Lewis acid in this case. The water's donating the lone pair, behaving as the Lewis base. SO2 does this to make sulfurous acid as well. Carbon dioxide does this to make carbonic acid. And so these pollutants that are primarily produced by combustion do produce acidic water. These pollutants can also dissolve in water streams and react with water to produce acidic waters, which is one of the primary problems beyond the global warming, but with climate change also is the dissolving of these combustion products in water, producing acids and lowering the pH of important water systems. And so that's an introduction to the concept of Lewis acid and Lewis base. You should be familiar with this concept, even though it's not a big focus in the class, you should be at least familiar with the definition where the Lewis base donates the lone pair and the Lewis acid accepts the lone pair. And that's the end for chapter 18. I hope I'll see you guys in office hours, and let me know if you've got any questions, and good luck on your homework and your quiz later this week. I will talk to you soon. Bye.